All right, welcome to Lecture 25B, entitled Modeling Using Dirac Distribution Functions. The material for this lecture comes from Reading Assignment 5, Section 2.1. So the objectives are to figure out how we can apply the Dirac delta distributions to model a scalar density rho for point, line, and sheet sources, how to apply Dirac delta distributions to model a flux density J for line and sheet sources, and how to calculate the integral of a scalar density and flux density when Dirac delta distributions are invoked. So the basic concepts and visualization skills in this teaching module that you basically will acquire are including how to model a point, line, and sheet source for irrotational field problems, how to model a line and sheet source for source-free problems, field-free problems, and thirdly, the technique for computing integrals involving Dirac delta distributions. As usual, the second slide is just a summary of the slides to follow, so we'll just move on. All right, so question of modeling point, line, or surface sources. First of all, consider a scalar function or vector-valued function which is infinite or undefined at specific points and zero elsewhere. Secondly, you would need to invoke distribution functions or Dirac delta functions to model the behavior of said function at the specific points in question. And thirdly, we're going to say that the distributions that we're considering are said to have even symmetry as to make the calculations easier. So here's an example of a Dirac delta distribution. In this case, we call it a Gaussian distribution. There are an infinite number of possibilities and combinations available out there. You choose the one that serves your purpose, usually for sake of making calculations easy. If you want to see basically an interactive simulation for this distribution, you can click on the link that you see over here. So the Gaussian distribution, again, delta of x, would have this form. It will involve a limit of this value a going to 0, 1 over a square root of pi, e to the minus x over a squared. And what we do is we let a go to 0. Now, if a goes to 0, this term goes to infinity, and the width of this sort of shape here gets smaller and smaller. So with a getting smaller, this peak gets larger and the width gets smaller. So effectively what you'll end up with a value of 0, except at x equals 0, that you'll end up this spike that goes to infinity. It's even because if you look at the area under the curve to the right of the y-axis, it's the same as the area under the curve to the left of the y-axis. And the units of the delta function would be 1 over meter. So they still have units, just 1 over meter. And so this is a limiting exercise which we use to define delta x. All right, so some properties of the Dirac delta functions, and because it's a limiting process, so 3 particular examples. If we take a delta function with argument x minus x prime dx, integrate between the upper limit and lower limit of infinity and minus infinity respectively, you always get a value equal to 1. This is a property of Dirac delta function. So it basically is infinitely large and 0 width at a specific location in space, 0 elsewhere. So at x equals x prime is where the Dirac delta function basically becomes undefined. All right, another thing to look at is the notion of even symmetry. If we integrate from minus infinity to x prime and from x prime to infinity, then these two basically will be identical. This basically captures half of the area under the Dirac delta distribution, and this takes up half the area. We know that the total integral from minus infinity to infinity is 1, and therefore by just going from minus infinity to x prime, we end up with a value of 1/2. All right. Thirdly, if we were to take some arbitrary function and multiply by a Dirac delta function argument with x minus x prime and integrate from minus infinity to infinity, this thing we call a sampler. What it does is it picks off the value of the function at x equals x prime. So we end up with fx prime. Again, if we look at the definition of delta x minus x prime, it will be 0 for x not equal to x prime and undefined for x equals x prime. Okay, a note here. The limits of integration are shown from minus infinity to infinity, but in actual practice, the integration result remains unchanged if you use values that are finite, but at least bracket the peak. So for instance, here's an example. You got minus infinity to infinity of delta x minus x prime dx. We know that's equal to 1, but we could have easily written this as x prime minus delta x and x prime plus delta x. So this basically says you're looking at one bound that's just to the right of the undefined function and one to the left, and this is more than this. Basically brackets the Dirac delta function. As a result, this integral will also be equal to 1. So this is typically what we would do. All right, so then let's look at distribution functions of filaments in cylindrical coordinates and point sources in spherical and polar coordinates. In this case, we're dealing with transformation of coordinates, so we're dealing with a radius, but radius is only defined for r greater than or equal to 0. And therefore, when we do an integration of a Dirac delta function in either one of these coordinate systems, we're only basically capturing half the distribution. All right, so the upper integration bound on R for cylindrical point sources in 2D or 3D, or filamentary sources in 3D, or spherical point source in 3D, can be some value slightly larger than 0 in order to capture the Dirac delta function. So for example, since again R is greater than or equal to 0, if we integrate from 0 to some value R just greater than 0 of delta R prime dr prime, this value will be equal to 1/2. All right, so let's look at some examples of a Dirac distribution. This would be for a filamentary charge density. So this would be a filament that extends to infinity, and charge density at each point along the filament takes on a specific value. If we now basically take a cross section and look down, in other words, in form of XY trace, it looks basically like a point source, right? Filament basic point source. And so how would we basically describe this in terms of Dirac delta function? Well, looking down, what you would see basically is the fact that the charge density has 0 value until you get right to the x equals 0, y equals 0, because we're presuming the filament basically is along the z-axis, so it passes through the point 0, 0. So that means this will basically start to peak basically right along the z-axis, at x equals 0, y equals 0. And this, of course, we've designed this Dirac delta function to be an even function, so you can see here when we just cut through, we see that this yellow region and blue region are identical in terms of area. So this function has even symmetry. So this would be described as rho equals delta r, and gives you 3D perspective. You can play a little bit with this as parameter A adjusts the distribution width, and so what will happen is as the width gets narrower and narrower, this basically starts to peak. We can also talk about, for example, a uniform cylindrical surface charge density. So this would be a cylinder extending to infinity, basically with the charge density just on the exterior surface, the cylinder having a radius r. So in this case, if we draw out the Dirac delta function, that means it's 0 until you get exactly to a radius of r equals r, and then it begins to peak. And so this, in fact, is just a trace of sorts. We only get to look at half of this cylinder, and you can see here on this side, this has even symmetry, right? And if you let essentially the width of this go to 0, which is basically by adjusting this parameter A, then this will start to peak. This becomes larger, and this gets narrower. So this is a way of visualizing a Dirac distribution for the case where we're dealing with a surface charge. And how do we model that in a cylindrical coordinate system? Rho would be delta r minus r. So at r equals capital R, which would be the radius of this cylinder, this is when the function blows up. So this is just a sort of a way of representing the Dirac delta function when we're dealing with a surface charge density. All right, so let's look at some examples in terms of how would you basically write out the charge density for a number of examples. If we have a volume distribution, then we use the symbol rho, and units is coulombs per cubic meter. The surface distribution, we're going to use the symbol sigma. That's coulombs per meter squared units. Line distribution, we're going to use symbol lambda. Units are coulombs per meter in either 2D or 3D. And a point charge will have the symbol Q and has units of coulombs in 2D or 3D. So if we look at this example, this is an infinitely long filament, and you've got a point charge here. If we were to represent this system in terms of Dirac delta functions, then rho would involve this quantity here, lambda, delta x, delta y, which corresponds to this filament. And this is a point charge, so this would be Q. It's a three-dimensional point, so there'll be three delta functions in this case. Delta x, because it's at x equals 0. Delta of y minus 2, y because it's displaced by 2 units along the y-axis, and basically it's at delta z. So this represents the charge density of the point source, and this term represents the charge density of this filament. Now let's take an example of a surface charge. So this cylinder would extend to infinity in both directions. So in this case, rho would be equal to sigma delta r minus 1, because it's a surface charge density. And this would be in cylindrical coordinates. If we're dealing with a volumetric charge density, and again, this would go to infinity. Let's say it's a uniform charge density, rho naught, within the radius 0 less than equal to r is less than equal to 1, and 0 outside of that region, then we would basically describe the charge density in this fashion here. Now, we've chosen an example involving charge, but you could have also had mass, in which case C is replaced by the units of mass in kilograms. All right, so here just a pictorial description of various scalar density, Dirac delta distributions for rho. So this is a point source, and so I could write this basically in Cartesian coordinates. It's just delta x, delta y, delta z. Units would be coulombs per cubic meter. I could also write it in spherical coordinates, in which case it would be written in this form, where this r now is just the radius. All right, infinite line, I could write it in Cartesian coordinates as lambda delta x delta y, or in cylindrical coordinates as lambda delta r over pi r, r of course being the radius parallel to the xy plane. If I'm dealing with a surface, planar surface, so this would be sigma, which is a surface charge density. This lies right on the xy plane, which means this is basically delta of z. This is a infinite cylinder, and in this case, basically, it's got a surface charge on it, and so in this case, rho would be sigma times delta r minus r, where r is the radius of this cylinder. And again, the units of rho remain always as coulombs per cubic meter. And here's a sphere with a surface charge. In this case, basically, it would be similar to this one, but now this r represents the radius that points in all directions in space. Here, the radius was only pointing parallel to the xy plane. All right, so the next thing is a scalar property derived from taking the triple integral of rho dv, which is nothing more than the total charge enclosed. I could have also used mass density rather than charge density. And so the units of the integrated scalar volume density rho do not depend on whether the function representing rho is differentiable, not differentiable, or a Dirac delta distribution. So let's look at a couple of examples. So Q, which would be the total charge enclosed, would be rho dv. A differentiable case, a non-differentiable case would be where we have to break it up into separate regions. So in this region it's differentiable, this region is differentiable, and this region is differentiable. Total charge enclosed would be just the sum of the three contributions if we're talking about three different regions. Let's now look at a 3D example. Point charge, surface charge, and a line charge. Different ways of representing the total charge enclosed. So if this was a point charge, we can either represent the point charge in Cartesian coordinates or in spherical coordinates. So in Cartesian coordinates, it would be delta x, delta y, delta z, if the point charge is at the origin. Similarly, if we want to expand, write this in spherical coordinates, then this would be the operative term representing rho in spherical coordinates. And we would integrate from 0 to r, where r just is greater than 0. And this would be total charge enclosed. So this or this will give you the same answer. It may be more convenient to use this formulation. What about a surface? If you have a surface, then the total charge on the surface would be surface charge density, delta z dz dy dx if we're dealing with a planar. This would be example if we're dealing with a charge on the surface of a cylinder. And this would be the charge if we're dealing with the charge on the surface of a sphere. So this is a total charge enclosed. And again, r basically just needs to be slightly larger than 0 in order basically in order to, it's just slightly larger than capital R, which is the radius of the cylinder, in order to basically incorporate the full cylinder. Similarly here, R needs to be just larger than capital R to incorporate the full extent of the sphere. And finally, we have the line. If we have an infinitely long line or filament, in Cartesian coordinates, the total charge on the filament would be just the integral of delta x delta y, because the filament pierces the xy plane, whereas along the direction z, basically, it can take on different values. We could also write this expression in cylindrical coordinates, in which case the rho would take on this form. And again, because r basically can only take on values greater than or equal to 0, all you need to do is have r slightly larger than 0, in which case you basically can capture the filament as a whole. So just again, a note, Q in this example represents the total charge enclosed by a Gaussian surface in units of coulombs. A Gaussian surface in this case basically would be is that the volume that we're dealing with, basically that volume basically will have bounding surfaces, and so through the divergence theorem we can link essentially the enclosed surface to the total charge enclosed. All right, so now let's look at the flux density J and look at the different types of distributions that we could have. So we could have, for instance, a 0D type of problem, which is a current filament. And if you were to take a trace, that would be basically equivalent to looking at a 2D point source. You could also have current flowing along a contour, in which case it would be a 1D type of problem. Or you could have current flowing through an actual surface, in which case it would be a 2D type of problem. In this case, if the current is flowing through a filament, then the current is I, and its units is amps. If the current's flowing through a contour, then the current density at any given point along the contour would have units of amperes per meter, and it's given the symbol J subscript S. On the other hand, if the current basically is flowing through the surface as a whole, then the symbol that's used is something other than JS or I. So it might be as a function of a distance. It could be constant, in which case it would be given some label, but it would not be a value either I or JS to make it distinct from the case of a filament source as well as a source basically on a contour. In the case of a 2D, through a surface, the units are amps per meter squared, or also can be written as coulombs per second per meter squared. So if we look at each one of these three cases, and for the first case, which is a filament which extends infinite distance in the positive and the negative z direction, if we were to try to understand how to characterize this current flux density, then in cylindrical coordinates it would take on the following form. It would be Bi times delta R over R, pi over R, and the current basically is flowing in the z direction. Now, if this were basically in Cartesian coordinates, then this would be, instead of a delta R, it would be a delta X, delta Y, if we're looking at a trace in the XY plane. On the other hand, if you have a current that flows through the sort of cylinder on the exterior surface, where the cylinder's radius is capital R, then in cylindrical coordinates, we can characterize this current flux density as having a z hat, being in the z hat direction, and it's a delta function, and to be r minus r. So clearly, when r is equal to r, is basically when there's a current, and then either on the inside or on the outside, there is no current flux density. So this would be a representation for this particular problem in cylindrical coordinates. And again, this current shell basically extends to infinity in both directions. The last case would be if you have a surface through which a current flux density flows, and this of course extends to infinity in both the positive and negative direction. Here it's clear that the current flux density is in the z hat direction. It's uniform within the range of 0 r to 1, and therefore you can state that J is equal to J naught z hat, J naught being a constant, and exterior to r equals 1. There is no current flux density, so this takes on the value of 0 z hat. You can look each one of these individual diagrams at the following link. Now we've chosen an example here which is involving charge in terms of current flux density, but could also have chosen max flux density, in which case coulombs would have been replaced by kilograms. All right, so let's look at a couple of examples here. So for instance, if we were looking at current flux density that's in a plane that's residing on the xy plane, then this is current flux density in the x-hat direction, and it's a surface charge density, so this would be delta S, and J of subscript S, delta Z. If we're looking at a line flux density, this is in the z-hat direction. We could either express this in terms of Cartesian coordinates, in which case this is delta x, delta y, or in cylindrical coordinates, it would take on a form that looks like this. All right, here we have a current flux density residing on the surface. So in this case, basically, we would have delta R minus R. It's in the z-hat direction. Again, J of S represents the surface current flux density, which has units of amps per meter. This is a case where the current flux density is in the circumferential direction. All right, so if we're dealing again with a cylindrical coordinate system, this direction would be representative of the theta hat direction. But again, it's on a surface, and that surface exists at R equals capital R. So this still is delta R minus R, and this is a surface current flux density, J subscript S. All right, so then next thing is the scalar flux property derived from this expression, J dot ds. Right, and units of J would be amps per meter squared. If this were a mass flux density, this would be units of kilograms per second per meter squared. Amps can also be written as coulombs per second. So there's some general guidance, and given a vector valued function J and a differential area element ds, the current flux I is defined by taking the integral of J dot ds over the surface of interest. And that generally would be essentially the surface is defined by the enclosed contour through Stokes' theorem. J dot ds is a scalar value function and represents the differential flux. The orientation of ds, the vector, with respect to J in Stokes' theorem problems is a degree of freedom. So you have some choice here in terms of how you select the direction. Typically, you want to choose J to be parallel to ds. Okay, again, because you want to make this integral simple to solve. The cosine depends the angle between the two vectors is removed, and so you get the cosine of the angles either 1 or minus 1. So this integral either has a positive value or a negative value. All right, so let's look at some examples. The units of the integrated flux density do not depend on whether the function representing J is differentiable, not differentiable, or a Dirac delta distribution. So for example, if it's differentiable, you would just basically integrate over S. On the other hand, if there are two separate regions, and each region is differentiable, then the total current enclosed would be the contribution for region 1 for the current and a contribution for region 2 for the current. If we're dealing with a Dirac distribution for a 3D object, then we have two options. We have, for instance, a surface. Could have a surface current. We can also have a filament current or a line current. If we're dealing with a planar type of object, right, then effectively, and it happens to be in the x-hat direction, the current flux density, then this is this integration that would have to be performed. And you'll notice here we have z just slightly greater than 0 and z just slightly less than 0. Why is that? Because that way we can capture the delta function. In this case, we have a current flowing along a cylinder in the axial direction along a surface. So here you have R prime minus R, the R, capital R being the radius of the cylinder. This is the Dirac delta function associated with it. This is a surface current flux density in terms of units of amps per meter. And of course, this is in cylindrical coordinates. And this gives you the total current enclosed. Circumferentially, the only difference between this one and this one is in this case, the current was flowing in the z-hat direction. Here, the current basically is flowing in the theta-hat direction. All right, so that's basically the only major difference that we're dealing with here. And also, if you look at the area vector, in this case, basically, it's a r prime d theta, whereas in this case, basically, it's dr prime dz and theta hat. So the area through which the calculation is taking place is different than the case for axial. Again, because we want the current flux density and the area vector to be pointing in the same direction when we're doing these sorts of calculations. All right, for line, the total current enclosed If it's Cartesian, this would be I times delta y delta x, assuming the current filament is along the z-axis. It's in the z-hat direction, and so this is basically the area vector points in the same direction, which is z-hat. Alternatively, we could have written this in cylindrical coordinates. In cylindrical coordinates, the area that we're differential area would be dealing would be r prime d theta. Current still flows in the z-hat direction, but of course the description of the Dirac delta function has a different form because this is in cylindrical coordinates. Notice again that all we need is for r to be slightly larger than 0, and you basically capture everything you need to regarding the Dirac delta function. So again, I in this example represents the total current flux enclosed by the contour in units of amps. And we use a closed contour because all these problems basically are going to be derived from an application of Stokes' theorem. All right, that concludes Lecture 25B. Thank you for listening.